Welcome to the last session tutorial session. So today we will discuss about the assignment number 8, and after that is a small assignment. So today we'll discuss about the assignment number 8. It's a small one, and after that you can ask question about any doubts which are regarding to the quantum mechanics and molecular spectroscopy course. And after that I can give a small brief overview that we have covered during this whole classes. Okay, I hope I am audible. Let's start. Okay.
Yes, sir.
My screen is visible. Okay. The first question is condition EMI So this kind of question, what we know for a transition to be happen, transition moment integral from selection rule, if TMI is 0, then forbidden transition. Where TMI is allowed. Now I hope in the class I think it's derived how this n and f value, difference between n and f value tells the whether the transition is allowed or not, but we can do it by using some trick. So if you take a odd function, a derivative integration of a in space, in the whole the space of a odd function, it will give you value 0. Okay, so now you can think that, so whatever the TMI is, psi f mu psi n. Okay, now if I take, now this mu is nothing but a dipole moment. You can think as a charge into distance, and if you take, so if you take mu, it will be, so this is also a odd function. Okay, so mu is a odd function. Okay, now depending on psi n and f, it will produce TMI value, and after that we have to integrate it, and that will tell whether this transition is allowed or not. Okay, so if this is odd, now if it transition from odd to odd, okay, then in case of that delta, sorry, there should be another column, delta n and result. So in that case your difference will be even. Suppose transition from 1 to 3 state, okay, then the result will be odd, so TMI will be 0. So this is forbidden transition. Now if I take, this is even, this is odd, this is odd. Now odd multiplied with odd will be even. Sorry, this is odd multiplied with odd will be even, and multiplied with even, it will be even function. So the result will be even, and it will be a allowed transition, or the TMI will be not equal to 0. Now if this transition you can think happening from 1 to 4, then the difference will be 3, so delta n will be odd. Now if I take odd and even, eventually your result will be even and TMI not equal to 0, and your delta n will be also odd. So 2 to 5 before transition, then your value will be odd number. Then both are even, initial state and final state are even number. Then your this difference value will be even, non-even function, odd function, even function. So your total result will be odd. So your TMI will be 0. So for TMI not equal to 0, the delta n should be odd. Okay, so with this we can say option number B is correct one. And similarly, if we take the option number C, psi 2 to psi 4, then the difference is even. So if delta n is even number, then TMI produce 0. So this is also this is forbidden. Psi 2 to psi 4 is a forbidden transition. Now if we consider psi 2 to psi 3, delta n, psi 2 to psi 3, now this is allowed because the difference is odd, and eventually the TMI value will not equal to 0. So this is a correct statement. So using this logic, we can say without deriving the whole integral, we can say what will be the result. Okay, now going to the next question. From So this question is about the rotational constant of isotopomers of HCl. Okay, so now if I start from the basic description of what I can say, B. So B. So let's say B0. So how we derive? E is equal to J into J plus 1 Now this value should be predicted in Hertz. Hertz means frequency, centimeter inverse. So if I look at the B0, that is H by 8 pi square I in Hertz unit. Okay, so now if we look at this value, if I decode the unit, so 8 pi square has no unit. This is I is nothing but mu into r square. The mu is reduced mass, so it will have the unit kilogram or kg, or r will be the distance, that is nothing but meter square. Okay, now the joule is nothing but kilojoule meter square second to the power minus 2 to s. So this is total is minus 1. So B0, so that unit of B0 will be in so if the expression B0 is H by, then unit will be in Hertz, and if B0 is H by 8 pi square IC, then unit will be Hertz. Okay, the because when you record the rotational spectra, it will come actually in centimeter inverse unit. Okay, so for that, this centimeter inverse unit is more practical rather than using the unit Hertz. Anyway, it can be converted by simply multiply the Hertz unit with 1 by c, that is the speed of light. Okay, so first option is therefore correct. Now the moment of inertia I is the same for both the isomer. No, because if we know the reduced mass, that is nothing but ma into mb, ma plus mb, reduced mass. Now the reduced mass for 2H35Cl should be greater than 1H35Cl, and moment of inertia is mu into r square. Okay, then I of 2H35Cl must be greater than I of Cl. So the I value, this moment of inertia, should not be same for both the molecule. Now what is written? B0 is rotational constant for 1H35Cl and B0 dash is rotational constant for 2H35Cl. Now the unit of B0 is the expression of B0 is 8 pi I, where we can think that all the part is constant. So we can think at B0 is inversely proportional to I. Okay, then as I 2H35Cl is greater than I 1H35Cl, then B0 dash should be smaller than B0. Okay, so the option number 3, B0 is greater than S, that is also correct one. Now if the electron density is changed, the number of electron is changed from 1H to 1H35Cl to 2H35Cl, then we can think that the bond length will marginally change, because only one electron is added. That should not hamper the bond distance so much. So there is change, but this is very negligible amount of change. Okay, so this is also a correct option. Okay, now moving to the third one. if you look at the vibrational frequency of a molecule, you can write it like this under harmonic approximation. You can write it like this: 1 by 2 pi K by mu, where K is force constant and mu is reduced mass. Okay, now what the force constant actually tell? Strength of the bond. If somehow the bond elongates, bond length increases, then the bond will be easily break down. Okay, then what you can say, that force constant will go down. Okay, so if bond length increases, then K value will be go down. Okay, so with this we can say that the force constant of, as I mentioned in the last question, that the bond length will marginally change. So if the bond length is changing, then the force constant value will not be constant. So therefore, on substituting 1h by 2h, means deuterium, the force constant will change. Okay, so with this option is incorrect. Now isotopic substitution of 1h with that of 2h does not affect the vibrational frequency of the molecule, as the force constant remains constant, which is also not incorrect, because I just discussed, as the isotopic substitution from 1h to 2h, the bond length changes, therefore the force constant will also change. And not only that, from 1h 35 Cl and 2h 35 Cl, there is a change of reduced mass, and it can be easily see that then the vibrational frequency is also depending on the inversely proportional to the root of the reduced mass. If the reduced mass is changing, then your vibrational frequency will also change, and the relationship is something like this. Okay, so therefore with this the option B is incorrect. Now looking at the option C, the vibrational frequency of 1h 35 Cl is greater than that of 2h 35 Cl, as it directly proportional to reduced mass. As I mentioned here, this nu is inversely proportional to the square root of the reduced mass, and mu of 2h 35 Cl is greater than mu of 1h 35 Cl. Therefore nu of 2h 35 Cl will be less of mu of 1h 35 Cl. Okay, so this option is also incorrect. Now let's look at the last option. The vibrational frequency of 1h 35 Cl is greater than 2h 35 Cl, as it inversely proportional to the square root of the reduced mass of corresponding molecule. That's what I told it here. Okay, with this option can be the correct one. Okay, now let's look at the fourth question. this question is talking about electronic excitation. Okay, so now electronic excitation, the transition, so first option is that transition moment integral corresponding to the electronic transition must be non-zero for the electron transition to take place. It is very straightforward and correct option. Otherwise, if it's zero, then there will be no transition. Okay, now the sum of the overlap integral of nuclear wave function must be equal to 1 for electronic transition. So nuclear wave function is telling. Okay, so if I look that excitation, so as I saw in the last class, so when if it a ground state and there is a excited state, now if I excite from here to vertically from here to here, okay, you can say these are the corresponding vibrational levels. Okay, and this is the vibrational levels for excited state. Okay, now one thing to notice that when it's getting excited, the while excitation, the nuclear coordinate did not change, so therefore the nuclear part is remains same, and if we take the sum of the square of overlap integral of the nuclear coordinate, that will eventually give you the value equal to 1. Okay, because it doesn't change while transition, so this is a correct one. Okay, now the sum of the next option is sum of the square of the overlap integral of nuclear wave function must be equal to 0 for electronic transition. If it equal to 0, then your TMI is nothing but is separated by nuclear part as well as electronic part. If the nuclear part is going to 0, then it will be multiplied with the electronic part, so whole TMI will be 0, so there will be no transition. Therefore this thing is also incorrect. Okay, now according to Franck-Condon principle, the principle vertical excitation, vertical electronic transition indicates the change of the geometry. Okay, so look at here. So suppose this is the bond distance of AB is R0. So now if I starting with V0 state of ground state 1, G ground state, now where it's falling to the excited state, so this is falling to the excited 1 2 3 4 5 6, so V6 state. So the V0 state of ground state, V0 ground vibrational level of G ground state is actually in has the maximum overlap or vertically excited to the 6th vibrational state of excited state. Okay, so in that case when it excites like the similar molecule A B with the bond distance R0, but because while excitation nuclear coordinate does not change, but now so geometry on while excitation doesn't change. Okay, so this option is also incorrect. So while excitation, the geometry will not change. Now I have excited the molecule from here, from V0 state to V6 state without changing the geometry. Now once I excited the molecule from V6 state, what it will do? It will start rolling down to the V0 state, okay, of excited state. Now the geometry is something like this. So if I take this thing, the bond distance will be something like R. So this bond distance increases. Okay. So while excitation, the electronic excitation is done on the vertically without changing any geometry. But after relaxation, it will fall apart to the minimized energy optimized structure which have a different geometry. Okay. So this is the main picture when one can treat a molecule when one can calculate the excited state phenomena of a molecule. So electronic excitation is not a is little bit tricky and it's not so straightforward. But one take home message is that while excitation, the electron always excited to the that state of excited from ground state to excited state where the geometry doesn't change, and this thing is known is called as vertical excitation. Okay. And if I take the difference between this and this we will call a diabatic excitation. Okay. So these are the two main features on electronic excitation or excited state ground state treatment. Okay. Now let's look at the last question of this assignment. option is saying the nuclear dipole moment depends weakly on the electronic coordinates. Yeah, that is okay, but is shown in the lecture, so I don't need to explain it more, because otherwise the TMI will not hold. Okay, now the second option is saying the in transition moment integral corresponding to electronic transition dipole moment contribution comes from nuclear coordinate only. That is not not obvious, not correct, because there is two part na, mu n and mu el, so both are contributing. Okay, now the third one, the in transition moment integral corresponding to the electronic transition dipole moment contribution come from nuclear and electronic coordinates. So dipole moment is only depend on the nuclear electronic coordinates, not nuclear one. Okay, so for this reason this option is also incorrect. And the last one, in transition moment integral corresponding to electronic transition dipole moment comes from the electronic coordinates. That is also correct. That is the correct option. So A and D are the correct option for the question number 5. With this we are done with all the assignments that are given in the tutorials, in the whole lecture session, and we are now done. If you have any question you can ask, and after that I will give a brief overview that whatever we have done with in this class. Okay, if you have any question you can ask me now. Hello.
Okay, sir, clear.
Okay, so now let's have from the first day what we have discussed. Let's do it one by one. Okay, so we have started with the simple phenomena of standing wave. So with the standing wave phenomena, what we have seen that if we have take a wave function that depends on two variable psi x and t. So one is the space and another is the time. Now for that standing wave, what we can write it something like d by dx2 of psi x comma t is nothing but 1 by c square d by dt2. Okay, so for solving that we use nothing but one trial wave function I alpha, where alpha is 2 pi x by alpha into x by lambda minus nu into t, which is nothing but a phase factor. And doing some quick first order derivation, what we come first order derivation with respect to derivative with respect to x and t, what we get 1 by h comma t dt is nothing but E, and IH cut ddx is nothing but Ex. So this is momentum operator. Now 1 by IH cut. Now if we write H, the total Hamiltonian is nothing but now for the most of the case, if Vx, hello,
Please show me the last page. Mobile. Okay.
so see now your potential can be dependent on both time and space. Now for a quick in that scenario, if we just think the Vx comma t, the potential is independent of time. Then this psi x comma t can be written in two product of space part and time part. Okay. Now if we do the this thing, it will nothing but give you what? Time dependent in your equation. Okay, so now if I solve it, it will give you value of 2 t, where h cut is nothing but h by 2 pi. Now the total wave function will be psi x into. Okay, now if I take the probability of psi x cut and xt, it will be nothing but psi x into psi x, so independent of time part. Okay, so that's what it's calling a stationary state. Okay, now with this is the foundation of whatever the time part and space part. Now the main motto of our the course was how to excite a molecule. So for excite a molecule, we need a operator that can add as a perturbation term on the Hamiltonian, and which helps molecule excite from one state to another state. So the preliminary criteria for a operator to excite the molecule from one state to another state was that if d, so time derivative of expectation of a time independent operator is, now if this value should not commute, then this operator can act as a excitation part. Means this operator can be used. So any conversely you can say like that, if the operator does not if the excitation operator does not commute with the Hamiltonian operator, then it will excite the molecule. Okay, so for excitation, what we did from the very basically what we did, we just take two body system, two state problem. So now, as I mentioned over here, is known that if this thing, then psi n will form a complete basis. Then any operator, any wave function can be written as a linear combination of a two wave function. Okay, so you not like that, you can write it psi 1 and psi 2. So we can denote the two wave function, two state problem. The wave function is something like phi is E1, which is a time dependent part, psi 1 and A T2 T psi 2. So the coefficient are time dependent. Okay, and now if I break it more, what we will get? Okay, now what we want to excite the molecule from state 1 to state 2. Okay, so for that, how it can be happen, we need to introduce some perturbative term in the time dependent Schrodinger equation. So perturbative term something like this. So we are working with phi, no? Sorry. Okay. Now there will be a big derivative, a little bit linear derivation, and with that, the result what we have got is something like this. The first derivative of E1, that is the coefficient of first state 1, is depend on the coefficient of the second state. Keep in mind, we discard these two integral because that perturbation in same state doesn't make any sense, because we are talking about the excitation. If after excitation the molecule in same state, and it cannot be said that molecule is even excited or not. Okay, similarly so now it is a two state problem where this two state problem, and if I look at the, if we look at the these two part, you can see both of A1 dot A1 and A2 are out of phase. So therefore when the probability is nothing but the square of uh, your coefficient. So when the probability of first state rises, the, in that same time probability of second state will decrease and vice versa, and therefore it shows a oscillation between the two state. So in a two state problem, if the coefficients are out of phase, then what we will get? We will get a oscillation like this. If it for a1t, then a2t something like this. So both are out of phase. Okay, and that will cause something called Rabi's oscillation. On the other hand, you can see that this is coupled differential of equation. And in the lecture session, it is also demonstrated how the coupled differential equation is converted to the in a uncoupled differential equation, which using some taking the double derivative of the coefficient, and which produces the value of these two terms. Where V star and V are nothing but these two terms. Okay. Now, if we solve it, you can found it can be shown that this value of A1 and A2. So, if we solve it, A1 and A2 using condition that at time t is equal to 0, a1t is 1 and the population and coefficient a22 is 0. Okay, so then you will get a value of a1 and a2, and from where if we take the square of a1t and a2t square, you will get the probability on a1t and a2. Okay, and if you plot it, you can get the oscillation of two states, something like that. Okay, so this is all for the two state problem. Okay, but the thing is that the two state problem is not the real case, because for a molecule there is a number of state in the number of state in their internal number of internal states. Okay, so for that the two state problem is two state to n state case. Yes.
Yes, excuse me, sir.
Yes.
I want to ask about the Hamiltonian. It is part of about Hamiltonian. That is part of Hamiltonian and unpart of Hamiltonian. How these two Hamiltonians are related? Are they comparable, or it cannot be predicted?
What? Okay.
About
see,
Hamiltonian.
See,
Part of
A0.
Hamiltonian and unpart of it.
Okay, A0, that is means unpart of Hamiltonian. That is only what it constitute. Is constitute only kinetic energy of electron, kinetic energy of nucleus, potential energy between electron and interaction between nucleus, interaction between nucleus electron and electron repulsion. Okay, this is the H0, which will you means without shining any light, this will already there. Okay, now if you are switching on the light, so light, what it will provide? Electric field and magnetic field. Now, and then what will happen? The energy of the system will change. Then how to measure it? So the Hamiltonian must be changed, no? Otherwise, the where the energy, from where the energy is coming, so that energy is incorporated in your perturbative Hamiltonian. Okay, so the perturbative Hamiltonian is nothing but the is not is actually due to the switching on the light. Okay, so now if you ask the relationship between H and HT, H0 and HT, I can only say that these two are not they are a non-commuting operator. Okay, but and the whole thing is that when the when the perturbative Hamiltonian is adding with the H0, means non-perturbative Hamiltonian, you can see some excitation. That is all. Am I clear, or is there any ambiguity in this?
Yes, it is clear.
Okay. Okay, now for the end state problem, we use the same treatment, and we use something called orthogonal property. And what we get with using this problem, we get the final state. If we denote as AF, then the coefficient is coming like this. T now if we take the probability, that is nothing but modulus of this thing, it will provide you the value of okay. So this is the first picture of a of a system when it's this is a first picture of selection rule. If this probability goes 0, there will be no transition from I to F state. Okay, so if therefore if this part is gone to 0, then there will be no excitation. But that this time we don't know what is the expression of H comma T. That is not known. Now the whole exercise is done. What is the expression of H comma T? Okay. Now as I told you previous sometime before, that what is H comma T? H comma T is nothing but is due to switching on the light on the excitation light. Okay, so now light, what is light? Light is electromagnetic wave. So it has an electric part and is a magnetic part. Now how to incorporate electric part and magnetic part in the H comma T? That is the second the question is now is coming. So for that, so electric field and magnetic field, and H comma T is a Hamilton, that is nothing but you can use as a potential. Okay, so potential, so we have to incorporate E and B into a potential, some potential. Okay, so that we can incorporate into H comma T. Now E has three factors, Ex, Ey and Ez, where B also has Bx, By and Bz. Now what we use for potential, from fixation from field to potential, we use scalar field and some vector field. So in the relationship in between scalar and vector field is something like that. Okay, so in Coulomb gauge, so in this kind of fixation is Coulomb gauge fixation. And there is another term extra, is this is 0 and this is also 0. So E is nothing but minus dA dt. Okay, so from there what we understood, that this plane wave A and E has same direction. But if A is a proportional to the cos omega t form, cos omega t is a cos, sorry, if A is a cos function, then if we take the time derivative, then what we will get, it will be a sine function, no? The time derivative will is nothing but electric field. Okay, with a minus sign. Therefore these two have a phase difference of pi by 2. So electric field and A has phase difference now. That is not our case. We need, what is the, we want to know what is the expression of this thing. That was our main target. So for that we use some Lorentzian force thing, because it is in a electric and magnetic field, where B is kept 0, then this thing comes to U into E. Now on the other hand, this is nothing but dA dt, and a force is nothing but another thing, is a time derivative of momentum. So what we get, P is nothing but Q into A with a negative sign. Now if we incorporate it in a Hamiltonian function, then what we will get, P0 mean without shining light, with shining light, and divided by m, that is give you the kinetic energy part and the potential. And doing some mathematics and tricks and using some formula, so what we will get, the ht comma is nothing but minus q by m a into p. Now using this equation, so what we can write now for this f comma f h comma ti is nothing but, so we need to know what this value. No? So for this value you can write this f q by m a into p into I. So for n number of system, what the h comma t becomes E0 omega cos omega t n qn by qmn unit vector into n. Okay, so this is called as electric dipole Hamiltonian. But now we need what is, but the dipole is not, what is dipole moment is not defined right now. We need to digress it more. So now going to much more further details, what we will get, this value is coming like cos omega t omega if by omega f into mu into e into I. Okay, so this is the value of your h comma t. So the one thing to note that not only the dipole moment, it also dependent on the electric vector. The transition dipole moment is also dependent on the electric field, direction of the electric field. So if a molecule is something like this and its dipole moment is like that, and electric dipole and the electric field of light is moving like that, then this value will be 0, there will be no excitation. So for excitation, mu dot E must not be equal to 0. So alignment is also a crucial factor. Alignment, or we can write like this, projection or alignment of molecule along the electric field direction is also needed, is also crucial for excitation. Okay, now this is a first thing for the first selection rule what we get. So mu should not have a mu should not be perpendicular to the direction of the electric field. Okay. Now the question is that what about this whole equation? Now this, if we write the whole equation, it comes like E0 square probabilities become mu if mu omega square zero to t dt e I omega if t cos omega t square into now what this term actually means, that is also we need. Okay, so for that what we use the simple approximation like that. If we consider light is from the time is plus infinity to minus infinity, but light is only on between 0 to t, so this is the time when the light is on, so we can write 0 to t is nothing but minus infinity to plus infinity, and using this equation and little bit more calculation, what we will get, this whole thing is E0 pi square by h cut square omega if by omega square 1 by 2 pi 0 to infinity dt square. Now this is as I this, if these two omega f and omega are conjugate, then we this thing can be written as two delta functions. I missed this. Okay, so this term and this term is talking about simulated emission and this is absorption. Okay, and this is transition moment integral. And now one thing to be noted, simulated emission and absorption cannot take place simultaneously. Okay, this is a thing that is always keep in mind, okay, that these two cannot be take place simultaneously. So once excitation is happening, then only excitation the emission will not happen, and vice versa. Okay, now the thing is that now these two are delta function. Okay, so that two delta function, if we take for absorption, is nothing but E0 pi square by h cut square omega square so this is for absorption. And this is a delta function. Now the delta function can be treated using same assumption. Okay, so it will become like this: E0 square by 4h cut square sine omega t by 2 whole square into now if we plot, what we will get something so this is omega f. Okay, so this is the 0 point, and that is called Bohr condition or resonance condition. So this is give us TMI, and that will give you the line shape. Okay, or line shape means line width, and that will give you intensity. Okay, now for that, now let's say rate of absorption. So if I treat absorption from 1 to 1 state, then so in now consider the rate of absorption in a multi level system. So the rate of the absorption is actually depends on the density. So this depends on only the density of the state. So if I excite from I to F state and F state is embedded with so many density of state, then the rate of the absorption is only depend on the density of the state of F embedded with. Okay, and this is known as Fermi golden rule. And that this is has a constant, and a constant okay, and the constant value is 2 pi h cut mu square, and the mu square is known as transition dipole, and the mu square has expression and all that is I have to write this term also. Okay, now this is for the rate of absorption and the Fermi golden rule. Now one thing is also needed, the Einstein coefficient, because see till now we have talked about emission, absorption and spontaneous stimulated emission. But if you excite a molecule, it will it will eventually decay after a time using some spontaneous decay process. So that should be incorporated while treating the molecule, while treating the excitation of a molecule. Okay, so if I excite a molecule, that is nothing but absorption, or you can say it stimulated absorption, because without stimulation molecule will not excite. Okay, now it can decay in two different processes. One is stimulated emission, one is spontaneous emission. Now at thermal equilibrium, rate of absorption is equal to rate of emission and rate of spontaneous emission. And based on this equation, Einstein come up with the expression of rate constant for spontaneous emission and the rate constant for simulated emission, which is nothing but where nu is nu is determined by the gap between the two states. Okay, so if nu increases, rate of spontaneous emission becomes much greater than rate of simulated emission. But what is the expression of A and B? That is we don't know. So for that we started with the Fermi golden rule, the rate of transition using Fermi golden rule, and we incorporate for a isotropic light how much if a molecule is aligned in a direction on z axis in only one axis, then how much of the total molecule will see the excitation light. Okay, and with this we come up this rate of transition sorry, rate of absorption is something like this, from 2 to 1 to 2 state transition. Okay, this is radiation density. Okay, now the thing is that we know all these things, and this is also proportional to, or it, right, maybe I can skip this thing also. Okay, so now in quantum mechanics you can think this n1 is 1, so A by B, so B becomes, okay, B become pi, B become pi by 6, pi by 6, okay, and if we know the B, the A becomes now good thing is that A is the rate constant for spontaneous decay. So this thing can be calculated using experiment. Okay, so if experimentally you can determine the A, then you can determine the B, and not only that, from if we determine the A, the transition dipole moment is can also be determined. So both experimentally and theoretically we can determine the value of transition moment integral. Okay, so now once we get this value, we now we are talking about the what will be the shape of the means absorption, the let's talk about the from I state to F state. Okay, so using some in light of Lambert-Beer's law, the this value is becomes I. Now if we give I is equal to UC by N, or eta is a refractive index, so this becomes NaH nu, nu rat nu because U is nothing but nu radiation d nu. Okay, so this is also expression of radiation rate of absorption. Now you can equate with the B value, so B value is also becomes like this, and eventually it is also have a value now. It gives the TMI value is by 2 So the TMI actually depend on this all are constant term, this integral. Okay, and is somehow depends on this something called extinction coefficient. Okay, now uh, the next thing is come the line shape. So two type of line shape is taught in this class. One is natural line shape, that is natural line shape, nothing but is a Lorentzian thing, and heterogeneous line shape, which is that is Gaussian. Now the Lorentzian Lorentzian line shape is only from there is when there is only one molecule and there is no interaction between the molecules. It's only homogeneous. The molecule is not interacting with another substance and anything. Totally ideal condition. Then the Lorentzian line shape will observe. But if the molecule is in heterogeneous condition, is interacting with other things, then the peak will be broadened up, and now it no longer the line shape will be no longer Lorentzian. Now it's become Gaussian kind of thing. So therefore, from this kind of plot, it becomes like this. Okay, so this is the Gaussian. So full width at half maxima, full width at half maxima, orange. Okay. Okay, and this value is 2 ln 2 to sigma. Okay, where sigma is the standard deviation of the distribution. Okay, so this is the two different line shapes, and now let's look at the with this. These are the different aspects of wave absorption spectra, and now let's look at the selection rules again, which is nothing but so this is the final expression that we got. Okay, now how to determine the selection rule? Okay, so for that, this mu part is the transition dipole is nothing is taken is derivative of bond distance. So it's a series that is in each step it is measured the distance at equilibrium, and it is known as Taylor series expansion. Now for vibrational case, so these things is can be written as and all. Now from this thing, that from this expression we can generate the selection rule for different type of excitation. So as we can see that for using this equation we get for vibrational excitation, vibrational case, that delta nu value plus minus 1. Okay, similarly the rotational case, this is plus minus 1 and delta k is 0. So delta k is for symmetric top molecules. Okay, symmetric top molecules, oblate and prolate and so many on. Okay, so these are the different aspects, that is and there is so many more. I have covered few of them, and for the exam purpose it will nothing but a MCQ. There is no need to do any derivation in for the exam. So you can just sum up the, means you can recapitulate the formulas that we get from the equation, and as you can see that most of the time there is very few questions are there where the expressions are needed. Okay, the most of the time what we need the essence what the expression means. Okay, and the most crucial expression, there is few expressions are there that you can you can memorize for the exam, and with this I think I have given the most this a little bit brief description of the course. There is so many else, and if I give all these things, the lecture will be very long. Okay, so actual the main purpose of the course was the how the molecule is excited, when it will excite, when it will not, and each cases how, and the thing is that how this excitation will determine by the selection rules, and how we come up with the selection rules, and there are few aspects of the few aspects of different kind of spectroscopies. Mainly it's covered rotational and vibrational spectroscopy, and it also gives the electronic excitation also. Okay, so with this I more or less I want to stop it here. If you have any question you can ask. Okay, so the forum is open, you can ask, otherwise we will stop it here. Yes.
Okay, sir. You can stop it here.
Okay.
Thank you.
Okay. So all the best for the exam. When is the exam date?
Next coming Sunday.
Oh, coming Sunday is close. Okay. I think it will help, and the question will be more MSQ type. Okay. So good luck.
Yes, sir. Thank you, sir.